In the last video, we have seen how moving clocks run slower and how the length of a moving object is contracted. If you haven't seen that video yet, here's a summary of what you need to know in order to understand this video. When you look at a light watch that is moving relative to you, that light watch is ticking more slowly when compared to your light watch. We showed that the factor by which it slows down is the relativistic gamma factor. Next, we showed that the length of an object that is moving relative to you gets contracted, which means that you measure a shorter length than an observer that is at rest with the object. If that object is at rest in system A and moving relative to system B, then the length measured in A is longer than the length measured in B, also by the same relativistic gamma factor as before. Today, you and I will continue our little voyage through special relativity. First, we will derive the Lorentz Transformation. After that, we will understand that simultaneity also has to be frame-dependent. And lastly, we're going to look at the invariant interval, which is an extremely important concept in relativity. As time and space are relative, the coordinates of an event depend on the frame of reference that you're in. An event is something that happens at a certain location at a certain time. So it is described by 3 spatial coordinates and 1 time coordinate. In this scene, for example, we start the light watch at t = 0, and we see a yellow sphere appear after 4 seconds, and it appears at a distance of x = 3.5 light seconds away from the origin along the x-axis. So that event can be described by the following 4 vector, and it could, for example, describe a spaceship turning on its engines or whatever. Now, as time and space are relative, different observers will describe the event with the different coordinates. So we will add a second coordinate system B, whose origin aligns with coordinate system A at t = 0. Observer B will also assign a time coordinate t' and 3 spatial coordinates x, y, and z' to that event. Our goal is to find a relation between the coordinates in A and the coordinates in B. So let's again look at that scene, and this time we're going to remember the position of coordinate system B at the time of the event. We can use that to get one equation that links the coordinates in system A and system B. These 2 distances here should be straightforward. The distance between the origin of A and the event is simply the x-coordinate of that event. And the separation between the origins of system A and B is given by the distance that B traveled in that time. So it's simply the velocity v multiplied by the time t of the event. This last distance between the origin of B and the event requires a bit more thought. We know that observer B assigns some spatial coordinate x' to that event, which is the distance from the origin of B to the event. However, it's not simply x', but x' divided by the relativistic gamma factor. To see why, remember what we learned about length contraction. X' is a distance that is measured in the coordinate system B, so you can think about it as an arrow that spans from the origin of B to the position of the event E. We are, however, currently describing everything from coordinate system A, and the length of that arrow in system A is going to be contracted by the gamma factor, because it is moving with respect to A. If that didn't yet make sense to you, perhaps rewatch the explanation one more time or go back to the last video that explained length contraction in more detail. Sometimes it does take a bit of time for these things to really settle and make sense. If you're good, then let's continue, because now we can extract the first equation that links the coordinates in A and B, because x' divided by gamma is the same as x minus v times t. And let's remember that equation. Now, we just looked at everything from the point of view of system A. Nothing can stop us from looking at the same thing again, however this time from system B, where now system A moved to the right, and remember the position of system A at the time of the event. As we're now in system B, these 2 lengths here can easily be expressed in the coordinates of B. The distance between the event and the origin is simply x', where now we do not need the gamma factor because we are in system B. The distance that A has moved from the point of view of system B is given by the speed v multiplied now by the time t', which corresponds to the time measured by a light watch in system B. Now, feel free to briefly pause the video to think about what this last distance here is. First, we know that the separation between the origin of A and the event E is given by x. However, we again need to remember that that length is contracted, because we're currently in system B. So we get x divided by gamma. From this we get another equation, and now we're basically done. All that's left to do is plug equation 2 into equation 1 to also get t prime as a function of the coordinates x and t of system A. I leave it as an exercise for you to show that it is equal to the following. This is the Lorentz transformation. For any event, we can now calculate its coordinates from the point of view of literally any other observer. It can also be rewritten as such, where this matrix is called a Lorentz boost. As we keep boosting along the x-axis, we can and will omit the coordinates y and z from now on. To give you another little exercise, the values that I use for the event in the animation are x equals 3.5 light seconds and t equals 4 seconds. The speed of b with respect to a is 50% the speed of light. Using our lovely Lorentz transformation, you can try and calculate the coordinates of that event in system B. I put the solution in the description. In the next video, we will see how the Lorentz transformation can also be interpreted as a rotation in spacetime that rotates from time into space or vice versa. Next, we will understand how the Lorentz transformation implies that two events that happen at the same time in one system do not necessarily happen at the same time in another system. To see that, let's define two events, first in coordinate system A. We place two observers at the same distance of 3 light seconds away from the origin. At time t equals 0, we send out 2 photons from the origin to those two observers. As they have the same distance from the origin, they will detect their photons at the same time, after 3 seconds. So the two events happen at the same time. The first event has the coordinates 3 seconds, 3 light seconds, and the second has these coordinates. Now, we can use the Lorentz transformation to calculate the time and spatial coordinates of these two events from the point of view of an observer B, who travels at 50% the speed of light. The result of that is shown here. And now you see something interesting. They do not happen at the same time anymore. The first observer will detect his photon sooner than the second observer. But why is that? Well, ultimately this again comes down to the fact that the speed of light is the same in all frames of reference. Let's look at this scene again from system B. From this point of view, the observer on the left of the screen is moving towards the photon, whereas the observer on the right side moves away from it. Therefore, it makes sense that the observer on the left detects his photon earlier, and the two events do not happen at the same time anymore. So, the concept of simultaneity is also frame dependent. And that is also something that requires a bit of time to fully digest, because it is something very much not intuitive from everyday experience. So, it seems like nothing is sacred anymore. Everything is relative and depends on your frame of reference. Space, time, simultaneity, everything. You might be wondering, is there anything that all observers can actually agree on? And that brings us to the last chapter of this video, the invariant interval. To understand what that could be, let's again look at a scene with two coordinate systems and two events. From the perspective of system A, the first event takes place at these coordinates, and the second event at these. We can again use the Lorentz transformation to calculate the coordinates of these events, as seen from system B, from where the scene looks, as you can see, completely different. Both the position of the events and the time where those events take place are different. So the notion of distance between two events seems to lose all its meaning. Observer A would argue that the two events are 3.5 light seconds away from each other, while observer B claims that they are about 1.7 light seconds away from each other. And they also measure two different time intervals between the two events. So is there anything they can agree on? Well, there actually is. Both observers A and B could agree on the same third coordinate system C, and then take the time interval or the spatial distance between the two events as observed from that coordinate system C. Now, it is always possible to go into a coordinate system where both events happen at the origin of that coordinate system, and we will choose system C to be that coordinate system. Let's see what that looks like. We see that both events happen at the origin of that coordinate system C. We can now look at this coordinate system C again, now from the point of view of system B, and once again we see that both events happen at the origin of our new coordinate system. Now, here's the important part. Both observers A and B look at a third system C, and that third observer is the same for both A and B. Let's see that that really makes sense for us. The two events that we keep seeing again and again are always the same events. For example, one spaceship turns on its engines and another spaceship turns on its lights. The events are always the same. We're just observing these two events from a different frame of reference every time, therefore assigning different coordinates to those events. But the events are always the same, which means that there can only be one such system where both events happen at the origin. Make sure those last few lines of explanation really make sense for you. Because now that all observers agree on one system C, we can go one step further. We imagine that observer C turns on a light watch when the first event happens and turns off the light watch when the second event happens. All observers can then read off the time of that light watch in system C. And all observers are going to read off the same time, which we're going to call a delta tau. And doing that from system A, we see that the clock of system C ticks almost 2 times. When looking at it from system B, we again see that the clock ticks almost 2 times, the exact same amount as before. To get an actual distance, we simply multiply that time by the speed of light c, which gives us the invariant interval delta s. So we found a notion of distance between two events that all observers agree on. Now, how do you actually calculate that invariant interval from any arbitrary coordinate system? We want to know the time that elapsed on the watch of observer C, and as that observer C is moving with respect to us, we know that her light watch slows down. So, while we in system A would say that the second event happens 4 seconds after the first event, we know that the observer in C would assign a smaller number to that, because her time slows down compared to us. In the last video, we derived by how much exactly her time slows down, when we talked about time dilation. We saw that it is scaled by the gamma factor, which, written out, is the following. The velocity v is the velocity of system C in system A, and it can be calculated using the coordinates of the event. It has to move at just the right velocity to be at the position of both events. Squaring both sides and doing some simplifications, we get the following equation for the invariant interval. As discussed, this is the same no matter which coordinate system you choose. So, using the coordinates of system B, or literally any other coordinate system, gives the same result. This is a frame-independent quantity that is invariant under Lorentz Transformation, and those are extremely important in relativity. We can also rewrite this in a slightly different form, again using matrix notation. The matrix denoted by n mu nu is called the Minkowski metric, and we're summing over both indices mu and nu using the Einstein summation convention. Also, we define x superscript 0 to be the time coordinate multiplied by the speed of light, which simplifies our calculations a bit. Also, I lied a little bit to you earlier when I said that you can always find such a system C where both events happen at the origin. Because it could very well be the case that both events are that far away from each other that system C would have to move faster than the speed of light, which is not possible. In that case, the invariant interval becomes negative, so we cannot interpret it as the time of system C anymore. But instead, you can now always find a coordinate system where both events happen at the same time. Then the absolute value of delta S is the distance between the two events as measured in system C. In the case where the invariant interval is negative, the two events are called space-like. When the invariant interval is positive, they are called time-like. If you manage to follow everything up to this point, you should now have a pretty good grasp of some of the basics of special relativity. In the next videos, we will spend a bit more time on some topics of special relativity.